Hello and welcome everyone to this second part of the fine-tuning. So in this part, we first want to generate the data which we want to use for fine-tuning using our paper about direction of arrival estimation. And then we will organize the scripts which we got from Anthlos in the previous video and run it using this new data. So let me start now by showing you how I generate my training data. So what I did is I went to ChatGPT and I clicked on this upload file, upload from computer. And then I used this PDF here, which is the paper we were looking at in our RAG video. This is uploaded here, and then I asked ChatGPT to give me 50 questions about the music algorithm and to save them in a CSV file. So ChatGPT did that, and I downloaded this CSV file, and then I asked to give me a summary about the music algorithm, and then I also added question about this summary. Then I did the same for the Esprit algorithm. So I asked to generate 50 questions and then a summary and so on. And those CSV files are saved here. As you can see, I put all the questions about the music in this one CSV file called music algorithm question answers. So you can see here we have like 57 questions, and for the Esprit we have like 54 questions. And this data I will be using for training the model, and then hopefully at the end I can ask any question I want about either of these algorithms. Of course, if you want to use this in production, you want to automate this step. So for example, if you are using ChatGPT, you want to use ChatGPT API and then automate the generation of the questions. So even uploading the files and the generation of the questions, so that it will not take much time for that. If you want to use open source models like using Ollama, then you also need to do that. So we already seen the code to query some models using Ollama. However, what you want to make sure here, if you want to use Ollama locally, that you really need a good model. So basically here we are training a 3.2 model llama with 1 billion parameter. So to generate the data for this model, it's better to use a larger model. So maybe like 400 or maybe 700 billion parameters model. So that you make sure that the data which you are generating is really of a high quality. That's already known. So that's like using a large model to train a smaller model. And once we got the data, we can really apply the fine tuning as we've seen from the previous part of this video. However, since this is like a repetitive task, I went a step further and I arranged this Ant+ code in functions. So let me go through that. So this would be this file here called Ant+ fine tune. So you can see here we have the imports as usual at the beginning. Then I started defining some functions. So this first function called prepare model, and for that you give the model name, for example llama 3.2, and the chat template. So basically here also would be 3.2, the maximum length, the data type, and if you want to do a 4-bit quantization or not. And this, as you can see here, will generate the model and the tokenizer, and do this also get BIFT model. Yeah, maybe I should also have exposed these two parameters here. So the rank of the approximation and the layers which we want to target. Yeah, maybe you want to do that. So this function will return for us at the end the model and the tokenizer. Then we have the function to prepare the data, and this function will take the path for the CSV files and the tokenizer, which is the output from the previous function. So here we have the two files, as you can see. So we list those files here, and then each time, as you can see, we are reading a panda frame and we are appending those to the list here. Finally, we are concatenating everything in one frame. Then we are converting to this panda frame to a dataset. Since I know that we have a question answer here, so I have made this smaller function here, which will take this question answer and change them to a content with a role user. So that would be for the question, and the content with the role assistant for the answer. And then we'll return it in the dictionary under a key called conversation. So that's really imitating what we've seen in the dataset from the previous video. So, and that's it. So really after applying this function, we already have our dataset with our own data, which we want to teach to the LLM. So the third function is preparing the trainer. So this is, as you remember, we have this SSF trainer with the training arguments. So here I'm only exposing the maximum sequence length, but maybe you also want to expose also these two parameters since they are important, and the number of steps also here. As you can see, the return here at the end of the function is the trainer. The next function is saving the model. Once got the path here, we are saving the model and the tokenizer, similar as the previous video. Then I have here a new function called merge and resave. So basically it will take the base model and the saved LoRa. So from the base model, we will get the weights, there's the pre-trained weights, so those may be like from Hugging Face, for example. And then here we are creating a new directory with a dash merged at the end. And inside this directory, we will save the new merged model. So basically, by merge here, we mean the base model, then merged to the LoRa. So we loaded the base model, we loaded the LoRa, and then we are calling model merge and unload, and then save pre-trained. So now this save pre-trained will save the merged model. So basically, pre-trained weights from the GitHub plus the fine-tuned LoRa. So that's basically the whole model which we need to do inference. Also here, as you can see, I'm like copying these 3 JSON files for the tokenizer to the merge directory, because in the next step, which is getting the GGUF model, I want to use them. So in this function will take everything in the merged folder, which has been saved the previous function here, merge and resave, and convert it to this GGUF format. Let me say a few words about this GGUF format. So this format is coming from the llama.cpp. So this is the GitHub repository for llama.cpp. This is made by Grigory Gerganov. Hopefully I pronounce it correctly. And the llama.cpp is a really great library used for running LLM models, and Ollama is even based on that. You can see here this llama.cpp has like binding in all languages. You can use it even in Python, in JavaScript, in Java, Rust, C#, so really most of largely used languages. And yeah, there are UIs, tools, and other stuff for it. And this llama.cpp is used in Ollama. So if we went to the Ollama website and let's go to the GitHub, and let me search for llama.cpp. So you can see that the supported backends for Ollama is this llama.cpp, which is founded by Grigory Girganov. This is a really great library, and the supported model format in this llama.cpp is the GGUF. The GGUF format is really essential for the quantized models, as you can see in this llama.cpp. So here they are showing you where you can download some of these GGUF files or how we can create them. So basically for creating those, we will use this llama.cpp repository, and there are some Python scripts which start with convert underscore, which we can use to do these conversions. So let me go a little bit up here to the files. You can see here we have convert Hugging Face to GGUF format, and also some other converting scripts. So I already have llama.cpp installed locally for me here at the D drive under programs, llama.cpp, and I have these scripts here. So if you don't have it, you need to download this llama.cpp somewhere, because we want to use these scripts here. So here you can see how you can build this project. So you really need to clone this project. So here you can see how you can build this project. Let's go to the how to build. And so you first need to clone, then you step inside the folder, and you really need just to make cmake and cmake build release. And that's it. I will show this in the future video, so don't worry about that if you did not manage to do it. And as you can see, of course, we need some software for that, so you need to have CMake installed. And since we are building, so we need a C++ compiler. So for me, I will be using the Microsoft compiler. I already have Visual Studio 2022 Community Edition installed for that. So really don't worry too much about llama.cpp if you don't know it for now. I will talk about it in the coming videos. So as you can see now, this convert GGUF function is really for outputting this universal format for llama.cpp. You can see here we are really running a command, and this command is like really Python, where I will be passing here as an input the path to one of these convert scripts here. So it would be really the programs, then llama.cpp, then one of these files depending on what I want to do, and then running this convert command with some parameters, for example, where I want to put the output file, or what's the name of the output file, and then the output type, which will also define the quantizations. So do I want to represent the floats as like F16, so that means 2 bytes, or quantization to 8 bits, so 1 byte, to make the models smaller. And that's it. So when we get this new model here, we can use it everywhere we want, so even in Ollama. Then there's also these tests, which we've seen also in the previous video from Anslas, so like verifying the mask, and of course testing the inference. So if we want to compare the new trained model with the older one. So that's it. So these are the helper functions. Let's go now to the main file and run those functions and compare the results. In the main file, as you can see, first step is as usual, I test the torch and if CUDA is available or not. And the output is true, as you can see here. Then here I'm importing all these prepare functions which we've seen before. Then I'm putting the path where the CSV files are. So this is the folder called CSVs. Then where I want to save the model, so I want to save it in models, then under DOA1. And the base model for that is Anthlas Llama 3.2, 1 billion parameter instruct. And the template would be Llama 3.2, obviously. So this is the length of the context, and this is the data type. So here I'm using F32, so float 32. So basically I'm not doing any quantization. So that would be during the training. I will do the quantization later when I convert to GGUF format. And now this is the configuration here for the conversions. So you can see now the script, it's in the programs llama.cpp and convert HF to GGUF. And I want the output file to be called the same as the base model. Then we have DOA and Q8 underscore 0 because this is the quantization which I will be using. So 8 bits. And we have like one question here. What's esprit in DOA estimation? And this question will be used to test the model before fine-tuning and after fine-tuning. So let me run this cell here. And now the next cell here is calling our functions from before. So as you can see, we prepare the model, then prepare the data, then prepare the trainer, verify masking, do the training, save the model, then merge and convert to GGUF. Let me run those. So you can see now it's faster here, the running, because we have less data than in the previous video. And you can also notice that the loss has dropped to 0.1 for the same reason, because we have like smaller data and we have enough parameters to really fit the whole data. So here we need to be careful. Maybe you need to test and see if we want to make the rank smaller. So in prepare model, maybe we want to choose a smaller rank. And of course, if you have more data, maybe you want to use a larger rank. That depends on your data. So you can see here now we finished. So here I'm getting error actually when I'm running this convert command from inside this cell. So what I do usually is I output the command here, so I can copy it and let me try to run it from here. But however, now I need to add the video 8 here to the command. So it would be like this, I mean for the paths and also for this path. And this will create this file here. So let me delete it so you can see that. And let me run now. And you can see here, so this GGUF file is already now created. As I said, we will use it in the future videos. Don't worry about that now. Let's go now to the final cell here, where we want to test our fine-tuned model against the original one. So we are taking the trained model and we are asking it the question. So what's split in DOA estimation? We are here. We are taking the original model and the original tokenizer, and we are asking the same question. So basically, what's split in DOA estimation? So let's run this and compare the answers. So let me make the space here larger. So this is the first answer here. It's saying that split is a subspace-based method used for DOA estimation, leveraging the rotational invariant structure, which is, I mean, a really good answer. So this is a correct answer. And this is from the fine-tuned model, whereas from the original model, so really directly from Llama 3.2 instruct, so it does not know what split for DOA estimation is. So you can see that it's already started like splitting this to two parts and saying it's like for radar estimation, and I don't know, a split for radar estimation method used in estimation of the radar signal in the context of directed oriented searching. So I would say it's maybe trying to invent something just to answer, and the whole answer is really wrong. Yeah? And the main goal of the estimation is, so it's really not answering correctly, and it's not even answering the question. While here in the fine-tuned model, we got our correct answer. So our fine-tuning is really working. And this really can be applied for any task you want. So if you have PDF files or text files or whatever data you have, so you can use ChatGPT or other bigger models to generate training data and fine-tune LoRa on this data. And of course, if you have multiple data sets or multiple clients and you want to serve them with different data, then you can have multiple LoRa's, and each LoRa is used for the corresponding client or the corresponding database as you want. So what I like about this approach is that your data is really now in the model, so you don't need to do the tricks which we shown in the previous video about RAG. So there we had to search for the data, and then maybe searching for the data, you know, in this vector databases will not give you the correct result. So that means no matter how good your LLM is, you will not be able to get the correct results. While here, your data is really encoded inside the parameters. So you don't need to do any steps. So really less delay compared to the RAG. So in the RAG, I mean, there's the search. There is also, if you want to augment the question, so you need to run the LLM to create another formulation of the questions or an approximate answer and then augment those. Or if you have agents, those agents will be communicating multiple times, and that's really will add a huge delay and computational cost. While here, all this is not needed. So you really just input the question to the LLM and the LLM will give you the answer. That's why I like this approach more. Of course, you have to be careful about overfitting the data and the problem called catastrophic forgetting. So that means you overfit your data and your model forgot what have learned before. And this can be controlled, as I said, from these few parameters like the rank of the approximation, the number of the training steps, and so on. So I hope you like this video, and in the coming videos I will talk a little bit about the llama.cpp, and I will also show you another variant of this llama.cpp called llama.java, because I like the Java programming language also, and that's why I will show you how you can create an AI assistant for the IDE from JetBrains for Java, so IntelliJ IDEA. So stay tuned for the next videos, and I hope to see you then. Bye.